Hello, myself Nobel Sahu, and here I will explain about among the following molecule which structure is a non-planar. Non-planar means if all the atoms of a species lies in a one plane, then that is called a planar structure, and if not, it is called non-planar molecule. Okay, so let's first take NO3 minus. Okay, so NO3 minus has a trigonal planar structure. Okay, so its structure looks like this. Okay, so it is a trigonal planar structure. Here all the atoms lies in a one plane. Okay, so I can show you with the help of this pen. Okay, so see, this is a trigonal planar structure. Okay. Give me a second. This is a trigonal planar structure. This one oxygen atom, this one oxygen atom, this one oxygen atom, this nitrogen atom. You can see clearly that all the atoms, that's all the four atoms lies in a one plane. That's why it is called planar structure. You can see like this also. All the atoms lies in one plane. So NO3 minus is a kind of planar structure. Okay. So let's move to the next molecule, that is H2O2. Now H2O2 has a open book structure. Okay. Its shape look like this. Okay. So in 2D it look like that all the atoms lies in one plane, but in 3D all the atoms not in a one plane. Okay, I will show you with the help of this pen. See, this is the structure of H2O2. So here you can see this is the open book structure. Okay, see, now it look like a open book structure. Okay, so you can see that here only three atoms lies in a one plane, that is one hydrogen, two oxygen. Okay, so only three atoms lies in a one plane. Okay, one hydrogen is above these three atoms. Okay, so H2O2 is an example of non-planar structure. Okay, so this is an example of non-planar structure. Okay, let's move to the next molecule, that is BF3. Now BF3 also has a trigonal planar structure like this. Here also, like NO3 minus, here also all the atoms lies in one plane. So it is an example of planar structure. Let's move to the PCl3. Now PCl3 is pyramidal structure. Okay, so it is a pyramidal structure. It is like this: Cl, Cl, Cl. That is one lone pair. Okay, so let's see that all atoms lies in one plane or not with the help of this pen. Okay, so this is, give me a second, this is the pyramidal structure. Okay, this is a pyramidal structure. Okay, so you can see that only three atoms can lie in one plane, that is chlorine, chlorine, phosphorus. But this chlorine atom cannot lie in a one plane. So this is also an example of non-planar structure. Let's move to the next molecule, that is XgF4. Now it has a square planar structure. It's like this: X, F, 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 one lone pair, one lone pair. So it is also a kind of planar structure. Okay, that is kind of a square planar like this: one lone pair above, one lone pair below. So you can see that all the all the five atoms lies in one plane. That is a fluorine, 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 and that is xenon. All atoms lies in a one plane. So it is an example of planar structure. Okay, let's move to the next molecule, that is SF4. Okay, let's take SF4. Okay, now it is a seesaw. It has a seesaw shape. Okay, like this. These two fluorine atom little bend due to this lone pair bond pair repulsion. Okay, so it is also an example of non-planar structure. Let's see how it is. Okay, so you can say this is the seesaw structure. Here two fluorine lies towards this and two fluorine are above, and this one lone pair. So here you can see that at a time only 3 atoms can lie in one plane, that is fluorine, sulfur, fluorine, or fluorine, sulfur. So at a one time only 3 atoms can lie in a one plane. So this is an example of non-planar structure. Okay, let's move to the XeO3. XeO3. It is again, it's a pyramidal shape. Okay, so it is a pyramidal shape. It is structure same like a PCl3. Okay, same like a PCl3. So if PCl3 is a non-planar structure, then this is also a non-planar structure. Okay, let's move to the pH4 plus. Now it is a tetrahedral structure. Tetrahedral structure. That is H, 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 H. Okay, so this is tetrahedral structure, that is structure of pH4 plus. Here also you can see at one time only 3 atoms can lie in a one plane. Okay, but these two atoms cannot lie in a plane. Okay, only these 3 atoms or these 3, you can take any 3. At one time only 3 atoms can lie in a one plane. Okay, so this is also an example of non-planar structure. Okay, so let's move to the next molecule, that is SO3. SO3. Okay, so this is the structure of SO3. You can see this is again a trigonal planar structure. Okay, so it is same like NO3 minus and BF3. Okay, so this is simply a planar structure. Okay, let's talk about the AlOH whole 4 minus. This is again a tetrahedral structure. Okay, this is again a tetrahedral structure, and it is same like a pH4 plus. Okay, so this is also an example of non-planar molecule. Okay, so out of these molecules, H2O2, PCl3, SF4, XeO3, pH4 plus, and these 6 molecules are non-planar in structures. Okay. Okay, so this is the second question. Here one species is given and two reagents, that is H plus heat and HBr. Okay, here I have to tell about the product. Okay, so let's see what happened. Okay, so see, this H plus is an electron deficient species. So now we have a 2 electron rich center, either this center or this center. Both are electron rich center. Okay, so both can react, but the probability of reaction of this lone pair is more as compared to this pi bond, because energy of non-bonding electron is more than energy of bonding electron. See, these pi bond are bonding electron. Okay, so it has a low energy. Okay, so this non-bonding electron has a high energy, so probability of reaction of this non-bonding electron towards H plus is more as compared to this double bond. Okay, so this will react first. Okay, after reaction it will form this species OH2 positive. Okay, so this will result in a very good leaving group, that is removal of H2 molecule, that is promoted by heat. Okay, so now you can see that there is another electron deficient center, that is carbon is generating, and here we have a, it is a kind of electron rich center. So this will again react with this carbon, like this. As a result, there is another carbon that is generated here. Okay, so let's number this one. Okay, so this is structure. Okay, so now this carbon again result in the formation of stable product. Okay, this product. See, all these steps are here will be in equilibrium. Okay, this step will be in equilibrium, this step will be in equilibrium, this step also will be in equilibrium, and this is the irreversible step which carry out this reaction towards forward side. Okay, so this is the first product that we get. Now let's see what happens when we react this compound with the HBr. Okay, so our first product is this. Okay, now let's react with the HBr. That is HBr. Here we can break as a H plus Br minus. Okay, so this pi bond is again electron rich center, and this is the electron deficient species. So this again attack on this H plus. Now here there are two possibilities, that carbon can be generated here, can be generated here, but this carbon is more stable because 3, 3, 1. There are 7 alpha hydrogen, and here if carbon is formed, then 1, 2, 3. So here if carbon is formed, then only 3 alpha hydrogen. So this carbon is more stable due to hyperconjugation. Okay, so carbon will form here instead of here. Okay, so now in this carbon, that is again electron rich center, that is bromide ion, will attack here, result in the final product, that is Br. Okay, so this is our final product. Okay, so let's write here. Okay, so this is the final product of this reaction. Okay, so now I will discuss about question number 7, that is about Balmer series. Okay, so in this question it is asking among four given option, which one is the correct option. Okay, so first option is the integer n1 is equal to 2. Okay, so let's see first. RH 1 by n1 square into square. Okay, so here in first option it is asking that integer n1 can be 2 or not. Okay, so see what happens. In Balmer series, let's take a hydrogen atom. Okay, so this is the energy, and this is the energy of hydrogen atom. Okay, so here we in case of hydrogen atom, electrons mainly lies in this n1 state. Now this is the principal quantum value of principal quantum number. So electron, in case of hydrogen atom, electron mainly lies in this ground state. So when we give energy, it will excite to the next energy level. On which energy level it will excite, it depends on how much energy we are giving. Let's suppose we are giving this much energy, it will excite to this level. Let's suppose we are giving energy to this much, then this electron will excite here. Let's suppose we are giving energy to this much, this electron will excite here. Okay, so let's suppose our electron can excite to anywhere depending upon how much energy, okay, we are giving. Okay, so it can go anywhere in any state. Okay, but there is one condition, that when it bakes, this is fixed, this is this is totally fixed. Okay, so when electron goes, let's suppose electron after excitation goes here, it will come back here. Let's suppose electron after excitation goes here, it will come back here, and so on. Okay, so see here, restriction is that n is equal to 2. So this is very important. Electron can go anywhere, but when it comes back to the n is equal to 2 state. Okay, so when it comes back, it emits radiation which is a particular frequency or a particular wavelength. Okay, so this radiation is detected by one detector. Okay, now this detector, what it will do, it will plot a graph between intensity and wavelength of that emitted radiation. Okay, let's suppose this radiation has a wavelength, this radiation has a wavelength, this, and so on. Okay, so there is a series of spectral lines corresponding to all this tension. This series is called Balmer series. Okay, so this is actually the Balmer series, in which this N2 can be anyone, but N1 is fixed, that is N1 will always be N is equal to 2. So first option, that is N1 is always will be 2, that is the correct option. Okay, so what is N2 here? N2 can be any state from where electron comes back, but N1 is always fixed in Balmer series, that is N1 should be 2. Let's check another option, that is option number B. Okay, so it is saying that ionization energy of hydrogen can be calculated from the wave number of these lines. So option A is correct, but B is incorrect. Why? Because it is saying that with the help of this line, can we calculate ionization energy? No, because in case of hydrogen atom, what is ionization energy? Okay, the amount of energy required to remove this electron from this cell to the infinity. Okay, so here when we remove electron from this cell to the infinity, okay, so that is basically the ionization energy. Means it is talking about N1 should be 1, then only we can calculate ionization energy. But here our N1 is N is equal to 2. Okay, so that is fixed. So this energy, when we, let's suppose here we are talking about this energy. Okay, let's suppose this wavelength coming from infinity to this one, then also we cannot calculate ionization energy from this, because if it comes from infinity to N1, then only we can calculate ionization energy. But here our radiation is coming from infinity to this. This is one of the example in which there is possibility that electron can come from infinity to, that is ground state. But due to this energy, we cannot calculate ionization energy, because this is the ionization energy. Okay, so option B is correct. B is incorrect. Ionization energy of hydrogen atom cannot be calculated from wave number of this line. Okay, ionization energy can be calculated with the help of this line only, but not these lines. Okay, so let's check third option, that is the line of a longest wavelength corresponds to okay, so in third option it is saying that longest wavelength corresponds to n is equal to 2 to n is equal to 3. Okay, so see, n is equal to 3 to n is equal to 2. Here energy is minimum. Okay, in this case energy is more, in this case energy is more, and so on. So as we move from this to this, always energy increases. But in this case energy is maximum. Energy is minimum. Energy gap is minimum. If this energy gap is minimum, then we know energy is inversely proportional to wavelength by the relation energy is equal to hc by lambda. Okay, so this energy gap is very less. So this energy corresponding to this energy there will be longest wavelength. So option third is also correct. Longest wavelength when electron comes from this to n is equal to 3D state to n is equal to 2 state, it emit one radiation that will have longest wavelength. Okay. So now let's check option number 4, that it is saying that as wavelength decreases, the lines of series converge. Means it is talking about this series. Okay, so this series is not, it's not like a parallel line. Okay, this series is actually I is equal to lambda. Let's talk about this. Let's suppose we are, here we have discussed in option number 3 that this line will have longest wavelength, then this. So this wavelength corresponds to, let's suppose, this lambda. Now this wavelength corresponds to this lambda. Now this wavelength corresponds to this. So as the energy gap increases, the wavelength, the value of wavelength decreases. So in this case, the line, the actual Balmer series will converge like this. Okay. So option 4 is also correct. So option A is correct, B is incorrect, C is correct, D is also correct. Okay. So option A, C, D is correct. Okay. So that's it. Now let's come to the last question, that is question number 8. Here I have to calculate the electrode potential for one reaction, okay, with the help of the reactions given in this question. Okay, so let's see how it will. So this is first reaction, that is 2 electron giving Cu, and it has an electrode potential value 0.34 volt. Okay, let's take another reaction. 1 electron Cu. This reaction has electrode potential 2. In this question it is asking that we have to calculate electrode potential of this reaction, that is Cu2 plus 1 electron, that gives Cu plus. Okay, so here I have to calculate electrode potential of this reaction. Okay, so to calculate electrode potential of this reaction, first try to generate this reaction with the help of reaction given in question. Okay, so let's try to generate this reaction with the help of these two reactions. Okay, so let's see here 2 plus 2 electron gives Cu. Reverse this, Cu plus 1 electron. Okay, so here I am not reversing this reaction, so electrode potential will be same, that is 0.34 volt. Okay, here actually I am reversing this reaction. Actually this is a reduction, so the electrode potential which is given here is the reduction potential. Okay, here I am reversing, I am making the reaction oxidation, so actually this will be oxidation potential. So it is a reduction potential, so oxidation potential will be, because reduction potential is a negative of oxidation potential. This is the relation between reduction potential and oxidation potential. Okay, so here with the help of this we can generate this reaction, that is these two can be cancelled out, 1 electron can also be cancelled out, and Cu2 plus 1 electron giving Cu plus. Okay, so you can see that with the help of these two reactions we can generate this reaction, but there is one problem. With the help of this electrode potential we cannot calculate electrode potential of this reaction, because we cannot add simply this standard electrode potential, because electrode potential is actually an intensive property which cannot be added. Okay, so for that there is one solution, that we know it has a relation with the standard free energy change, that is standard free energy change is equal to minus NF E naught cell. Okay, so that is the relation between standard electrode potential and standard free energy change. Now that free energy change, standard free energy change is a type of extensive property, means we can add this standard free energy change. So what we will do, first we will calculate standard free energy of this reaction. Now this reaction, after this we will add this standard free energy change for this reaction. From that we can calculate standard electrode potential of these reactions. Okay, so now let's see how it will. So let's suppose this is the standard free energy of first reaction, that is minus. Okay, before that in a P naught cell. Okay, so actually this corresponds to number of electron for the reaction. This corresponds to Faraday, which is a value 96500. That is showing charge on 1 mole of electron, and that is a standard electrode potential. Okay, so let's calculate standard free energy change of this reaction. That will be here there is 2 electron Faraday, and its electrode potential value will be 34 volt. Okay, let's calculate delta G naught 2. Here it is 1 electron. Okay, so minus 1 electron Faraday, that is minus 0.522. Now these two will be cancelled out and giving 0.522 Faraday. Okay. Okay, now add these two free energy change. Let's suppose this is a standard free energy change of a third reaction. Okay, so this will be sum of delta G naught 1 plus delta G naught 2. Okay, so corresponding to this we have a minus NF E naught cell, and delta G1 comes out to be 0.68 Faraday, that is minus 0.68 Faraday, that is comes out to be 0.522 Faraday. Okay, so here the N value for this reaction is 1. Okay, so actually it comes like this, and after calculation you will get E naught cell is equal to 0.158 volt, because this Faraday can be cancelled out, and after solving this you will get this value, and that is the standard electrode potential for this reaction. So by adding standard free energy change of the given reaction, we can calculate standard electrode potential for another reaction. That's it. Thank you.